Can you guys see the screen?
Yes, sir.
Yeah. So welcome to this lecture. This is lecture number 35 as per the course, and this is from module 4. And today we'll be starting with the voltage shunt feedback amplifier. And before that, we'll try to complete certain aspects which were left out in the previous class. And to begin with, yeah. We sort of try to understand different aspects of the feedback amplifier concept, and we have derived the input resistance RIF with feedback, the output resistance ROF with feedback, and then we also try to understand the bandwidth concept, the concept of bandwidth, and wherein we have clearly seen the picture of the break frequency. What exactly it means? It is that frequency where the gain drops from whatever the gain it has at 0 frequency to its 3 dB lesser frequency. That is the break frequency. And since op amp being uh, a feedback amplifier, it has got a single break frequency, and then we try to compare the break frequency of an feedback amplifier and to that of without feedback amplifier. So basically we try to compare F0 and FH. So F0 is the break frequency that we achieved for a simple voltage amplifier without feedback, and FF is the break frequency that what we have with feedback. And when we compared, we obtained FH, that is what would be the break frequency of an feedback amplifier, and that resulted into FH. FF is equal to F0 multiplied by 1 plus A beta. So that also means that the bandwidth of the op amp, or basically the bandwidth of the amplifier with feedback, in this case it is voltage series feedback amplifier, is greater as compared to without feedback. So now why this is very required? That is required because we have to ensure the gain remains constant for longer duration of time, and in that aspect feedback is going to play a crucial role. Now the next one amplifier whatever we are going to concentrate here is the inverting amplifier with feedback. Now please remember, whatever the amplifiers we are studying now, they are all the voltage amplifier, and that too specifically op amp is the main device that we are using, and the one which you have learned in the earlier class is your non-inverting amplifier, and that was your voltage series feedback amplifier. Now again, why it is called as specifically the voltage series feedback amplifier, I'll try to explain when I try to deal with the feedback amplifiers exclusively in module number 3. But now you just remember it is also called as voltage series feedback amplifier. Which one? The non-inverting amplifier, which we have dealt till date. Today we are going to start with the inverting amplifier with feedback. Again, the same concept. We are going to use op amp as the main device, and this particular arrangement is called as voltage shunt feedback amplifier or voltage parallel feedback amplifier. So this is how the circuit looks, and since it is an inverting amplifier, definitely the output will be the inverted one. Like if I give the input this way, the output will be the amplified version, and it will be having the negative value, and that's the reason you can see over here the input is given to the negative terminal. And if I just want to explain the arrangement, it has got a feedback resistance which is connected from the output to the input side. And where is the input connected? Input is connected to the negative terminal of the op amp, and hence output between output and the V2, which is your negative terminal, RF is connected. And to figure out the output, we have the load resistance, and the input source is grounded, and same is the case with the load resistance, which is grounded, and that's the reason I have shorted over here. Now whenever we try to understand the concept of feedback amplifier, we said the gain of the feedback amplifier is given by A divided by 1 plus A times beta, right? And now this beta is what is basically the feedback network. So this beta here is nothing but your RF over here, whatever, because it is that RF that is coming in the path between the output and input. If you can remember the voltage series feedback amplifier, if I just scroll up and if I can show you here, the beta was entirely made up of this entire thing. There it was a combination of R1 and RF, but whereas here the beta is only made up of, or the feedback network is consisting only of RF. Fine. So if I want to try to do the analysis, let's try to do it. Now a simple, we'll try to apply, since a lot of currents are flowing over here. Let's try to take the analysis by utilizing the Kirchhoff's current law. Now if I want to use the Kirchhoff's current law, I can sense there is a feedback current, there is an input current, and there is a bias current IB1. If you can remember in your previous courses, basically in your basic electronics courses or in your third semester, the input bias current or input bias voltage or output offset current of offset voltages are those certain parameters that will assist the op amp in the proper functioning of the entire circuit. Or basically, if I want to ensure the op amp to work as a perfect amplifier, I need to be taking care of the offset voltages, bias currents, and these bias currents are basically those currents which are resulting because of certain transistors that are present inside the op amp. So bias currents is that. Now since there's only one bias current which is coming over here, and that it will be definitely having a value of 0 because it is connected to, the current cannot enter the op amp because of the high input resistance. Fine. Now there is one more bias current over here, IB, which is entering over here. The IB1 is over here. Now like I was telling, from Kirchhoff's current law, I in is basically nothing but current entering this node is equal to current leaving the node. Current is leaving here and current is leaving here. So basically I in is equal to IF plus IB. So that is basically my equation number 1. And since the input resistance of the op amp, which is my input resistance, it is not the R1, it is the resistance which you can find over here. Since the input resistance of the op amp is very, very large, IB will be very, very small. Or to some extent I can say I can ignore IB, that is the bias current or base current. So in that scenario, if I just ignore this, then that makes my IN is equal to IF. So if that is the case, then my entire equation will turn from IN equal to IF plus IB to IN equal to IF. Now, since I have two currents which are equated, let us try to express both the currents in terms of voltages. Now here I'll be using Kirchhoff's voltage law. Now if I just say, if I can just tell you, just a moment. Yeah, if I just give you a glimpse of what exactly Kirchhoff's voltage law or how exactly it is going to work. Please remember, if I have two terminals A and B and the resistance marked as R, and the current is I. Normally, if I ask you what is the current that is flowing through this resistance, you say voltage is applied as V. Let's say terminal A is having applied a voltage of V and terminal is grounded. And this is a resistance and current is flowing over here. Kindly excuse me for the filthy drawing because I'm using the mouse, so that's the reason the drawing is not so good. And normally, if I ask you what is the current flowing through this resistance R, you basically apply the Ohm's law. So what is usually you say V is equal to IR or I is equal to V by R. So that's what your answer. So basically I is equal to V by R. Now this is the same law that we are going to utilize over here, and basically the Kirchhoff's voltage law is nothing but the extended version of the Ohm's law. How it is working as an extended version of Ohm's law, let me tell you. It is not V by R, it is always the highest potential minus the lowest potential whole divided by across which the resistance is placed. Now the highest potential here is A, which is connected at V, and the lowest potential is B, which is connected at 0, and then we divide the entire term by R. Now, because it is understood that 0 is the ground, and we do not consider this 0 in while writing the equation, and hence we always try to ignore these things and we write just V by R. So this is how basically the Ohm's law works. Now V1 and V2 anta kottidandre, then your Ohm's law equation would have been I is equal to V1 minus V2 divided by R. So V1 value ಎಷ್ಟದ ಅಂತ substitute ಮಾಡ್ರಿ, V2 value ಎಷ್ಟದ ಅದನ್ನ substitute ಮಾಡ್ರಿ, and then you will get the value of Correct. The same principle I'm going to utilize over here. And since I am quoting I in equal to IF, what is I in? I in is flowing from the input source V in here. So it is flowing from V in till V2. So basically that makes my Kirchhoff's voltage law or Ohm's law as V in minus V2 divided by R1, because I in is flowing through R1. So that's what I have written over here. And the same thing if I want to write about RIF. IF is flowing from V2 node till V0 node. So this is V0 node. And in between V2 and V0, RF is present, through which the current IF is flowing. So that makes my Ohm's law or Kirchhoff's voltage law equal to V2 minus V0 divided by RF. That's what I have written over here. And please try to ensure you consider the direction of the current, and current L in the starter, that node will be taken as first. As simple as that. I hope it is making it clear. Now this is my Kirchhoff's voltage law. I am expressing I in and IF. Now let's try to simplify it and get it an expression the way how we have obtained the expression for the non-inverting amplifier or voltage series feedback amplifier. Fine. Now before that, I sort of want to understand what exactly will be the value of V2, because V in is in my hand. Whatever input voltage I am going to give you, I know it. R1 I know it because I'm going to put it in the circuit, and RF also I know it. It is in terms of mega ohms. I know it. V0 I'm going to obtain it once the entire circuit completes the operation. What about V2? V2 is an intermediate voltage, and right now I don't know what is V2. But to understand that, let me try to utilize the aspect of V0 equal to A times V1 minus V2. This is the simple voltage equation or the output voltage equation for the op amp. Basically, we say on the op amp amplifies the difference between the inputs, which are nothing but V1 and V2 in this case, with a gain A. And if I bring A down to the numerator denominator over here, that makes V0 by A is equal to V1 minus V2. Now, because V1 is connected to ground, so don't confuse this with a VDD or VCC. This is ground actually. So this is ground. Because V1 is at low potential, so that makes this to be 0. So that in turn makes what? V0 upon A is equal to minus V2, or V2 equal to minus V0 by A. So that gives me the value of V2. So which makes, now I know V in, I know V2, I know V0 will be V0 now, and R1, RF will be, I'll be keeping the value as it is. Now if I can substitute these values over here in this equation, so V in I am keeping it as it is. In the place of V2, I am keeping minus V0 by A, which I obtained just now here. And again is equal to V2 is what? Minus V0 by A, minus V0 whole divided by RF, here whole divided by R1. So this is what my equation I'm going to get now. So let me try to simplify this. What I'm going to do is I'm going to push this RF to LHS, R1 to RHS. And if I do that, V in plus V0 by A multiplied by RF minus V0 by A minus V0 multiplied by this R1 will come over here, R1. V in times RF, I'm just simplifying it. And then I'm pushing this V0 to RHS, because I just want to ensure all the V0 terms are collected at one side and all the V in terms are collected at one side, because right now in the equation I am just having two voltages, one the V in other, one V0 other. So just try to bifurcate both the voltages across two sections. Fine. So cross multiply ಮಾಡ್ತೀನಿ V0 upon A, I'll push it up to the RHS, that is V0 upon A multiplied by RF, that will be minus this time. Here on the RHS it is minus V0 by A minus V0 multiplied by R1, and the LHS it is V in times RF. So let's try to simplify. This becomes minus V0 by R1 minus V0 R1 by A minus V0 RF by A, and at the LHS it is V into RF. And if I take out V0 common, that makes that gives me R1 plus R1 by A plus RF by A. And I'll try to sort this, or try to re-simplify it by making the denominator to be equal to A. So LCM Thonduna, if I do the simplification, that makes me AR1 plus R1 plus RF divided by A multiplied by V0. Now I'm interested in finding out the gain, because what is that I started with? I started with this is a closed loop This is a closed loop gain that I wanted to highlight. So if I want to understand, or if I want to obtain the gain, what is the gain? Output by input. So here is my V naught, here is my V in. So what I'll do, I'll bring V in down over here, and I'll bring this entire term down to RF. So that gives me, and this will be multiplied with RF. It's a simple simplification. So basically I'm pushing A towards LHS, and I'm bringing the numerator term which was present in the RHS down to the denominator. So that gives me V naught upon V in is equal to ARF, minus term will be there as it is, ARF whole divided by, because since it is coming down to denominator, that gives you AR1 plus R1 plus RF. So this is what is the standard equation for inverting amplifier with feedback, or voltage shunt feedback amplifier, or voltage parallel feedback amplifier with op-amp. Now you may ask the question, so this is not the expression that what we have learned in the basic electronics course. We learned that inverting amplifier and the equation, it was minus RF by R1. What is that? Here I am getting it as minus A times RF divided by AR1 plus R1 plus RF. That's the reason I'm calling it as an exact value. Exact value antandrenu, this is the practical value of the inverting amplifier's gain equation. And the gain equation what you obtained as minus RF by R1, it is the idealistic value, wherein the gain only depends purely on resistances. But whereas since op-amp is behaving as a feedback amplifier, the gain has to depend on the term A, and this is what is my exact equation. So please try to remember this. This is ARF divided by AR1 plus R1 plus RF. So this is what is the gain equation. And negative sign indicates that it is 180 degree out of phase. And because you have given the input to the negative terminal, the output has to be inverted by 180 degree. Now, how do I make this equation look like this? That's what I have done over here. Now, you know that the A value, that is A is what? Open loop gain. Please remember, always A will be very, very large and RF will be very, very large. Other the value you can take it in terms of mega ohms, in terms of 10 raised to 6 or 1 into 10 raised to 6. So A times R1 will be very, very large as compared to R1 plus RF. And if that is the case, then I can eliminate R1 plus RF, or I can ignore R1 plus RF. And since I'm dealing with an ideal case, I can do all these assumptions. So if I do that, what is that is left out? Minus AR1 divided ARF divided by AR1, and AA cancels out. This has been eliminated already. What is that is left out? Minus times R1 RF divided by R1. So this is the ideal value of gain equation what you have obtained in your previous courses. So this is how the gain equation looks. So that's all about your voltage shunt feedback amplifiers closed loop voltage gain equation. Now if I can just go back and try to give you the glimpse of the closed loop gain equation for the non-inverting amplifier. Yes, here it is. This is what is the exact value that I have obtained. A times R1 plus RF divided by R1 plus RF plus AR1. Denominator won't change. It is exactly the same thing. Only numerator is changing. Here it is A times R1 plus RF. Here in the inverting amplifier it is, oops, where it is? In the inverting amplifier, it is A times RF. There it is A times R1 plus RF. And another difference is negative sign. So it is quite simple to remember. Now, why I am insisting you to remember it, because there are some numericals that will be coming in the subsequent lectures, and we are going to ensure that these concepts, whatever we are learned, voltage series feedback amplifier, which is nothing but your non-inverting amplifier, and voltage shunt feedback amplifier, which is nothing but your inverting amplifier, which we have learned today. Along with these things, closed loop gain equation, Rn equation for both inverting and non-inverting, Rout equation for both inverting and non-inverting. So altogether 6 derivations you are supposed to remember properly. And based on that, there will be 1 or 2 problems that are going to be asked in the examinations as well. So that will help you in clearing the concepts when you solve the numericals. Definitely we'll solve some of the numericals once we complete these concepts. So this is all about the closed loop gain for the the inverting amplifier with feedback or voltage shunt feedback amplifier. Now let's just move ahead and try to obtain the concept of input resistance, how exactly the input resistance with feedback for the voltage shunt feedback amplifier looks, or basically Rin for inverting amplifier. Now before that, the same concept of virtual ground. So virtual ground concept in ideal mechanism. So basically I can obtain the equation of Ilian equation mantala V naught by Vin. I can obtain the same equation from the concept of virtual ground. How? You can see over here. Anyhow, I now know that In equal to If, because Ib is very small, or it cannot enter the op amp, and In equal to If. So idana nanu in terms of voltages express madide. Vin minus V2 divided by R2 R1 and V2 minus V naught by Rf. And I did a lot of derivation over here. Instead of that, what I can say, from the concept of virtual ground, if one of the terminal is connected at one particular voltage, let's say here the V1, which is your the voltage where you are not given the input. So E V1 ground connect agittu antandra ade similar point node here, that is V2, it will also be connected to ground. So this is the basic concept of virtual ground. So E concept na apply madidre, since V1 is 0, V2 will also be 0. So V2 will be 0. V2 will be 0. If I do that, what is that I'm going to get? Look here. V2 is 0. V2 is 0. What is that I'm going to get? V in by R1 is equal to minus V naught by R1. And if I do the simplification, what is that I'm going to get? The ideal value of minus Rf by R1. That's what I obtained over here. Ideal value of the gain minus Rf by R1. So that's how the concept of voltage or the virtual ground concept, or the gain expression from virtual ground concept, can be utilized in finding the gain for voltage shunt feedback amplifier. And this is the idealistic way of getting the gain, but the practical value of gain, anyhow, you have to remember this particular term here, exact value. Fine. Now the input resistance of the voltage and feedback amplifier with feedback, how exactly it is going to look, and how the circuit varies as compared to your previous circuit. We'll try to see that. Now let's try to rewrite the circuit, and since the voltage is, or the input is given towards the inverting terminal, so here is the circuit thing. And now there are, you can see there are some arrangement. The Rf which was here, right? The Rf value which was connected over here, now you can see that Rf value is not present. Now where exactly it has gone? Now to find the input resistance with feedback here in voltage and feedback amplifier, what we are applying is the concept of breaking an intermediate resistor, that is Rf, into its Miller components, or basically we are applying the concept of Miller's theorem. Now you may ask, what exactly is the Miller's theorem, sir? Where did this arrive from? So to understand what exactly is the Miller's theorem, so basically Miller's theorem, I'll just give you a small glimpse. A big resistor can be broken up into its two small components whenever you have a circuit arrangement where you can sense the input and output, and the resistance is in between the input and output. So our type arrangement iddaga, that resistance will be broken down into two components, which are called as the Miller components. And those two components right now here are your basically Rf divided by 1 plus A, one component 2, and inondu Rf multiplied by A divided by 1 plus A. One is towards input side, one is towards output side. So rather than having a center Rf here, I break it down into two components. How we have broken this in terms of this, either the value exactly hinge hang bantu sir, we'll try to study all these things when we come to the concept of purely the concept of feedback amplifier, or when we try to understand the Miller's equation in when we deal with respect to the frequency analysis of MOS amplifiers in module 1 or module 2. Alli bandaga we'll try to understand in detail about the Miller's circuit components or Miller's components. But right now, you just remember big resistance can be broken down into two small components arranged, one at the input side, one at the output side. Now here I'm not going to show you in detailed analysis of the input resistance. It's a very simple analysis. Now you may ask why this thing has been broken down into two components when we have not done it in the case of voltage series amplifier. Now allinu ಮಾಡಬಹುದು, ಅಲ್ಲಿ ಮಾಡಿದಾಗ if I use the Miller's theorem in voltage series amplifier, the analysis ಒಳಗ if I break the bigger resistance into two small components in the non-inverting amplifier in my earlier amplifier, ಅಲ್ಲಿ ನನಗೆ analysis ಒಳಗೆ ಏನು difference ಆಗಿಲ್ಲ. I don't find any reduction in the mathematical analysis. But whereas here, if I the moment I do it, I can see a huge reduction in the mathematical analysis. So that you can see over here. Now just look over here. Since I am interested in finding out RIF andrenu, that is the input resistance with feedback, and you are looking from the input side into the op amp. Idna nodadaga, if I can just look into clearly, I can see this resistance and Ri, they are in parallel, isn't it? RF divided by 1 plus a parallel Ri, and these two in turns are in series with R1, right? So if I can just mention that expression, that is RF divided by 1 plus a in parallel with R1 whole series with R1, RF divided by 1 plus a parallel with Ri whole series with R1, if I just do that, the job is done. That itself gives us the input resistance of the voltage shunt feedback amplifier with feedback. And this is what is the exact value equation for my the input resistance. Whereas what was the input resistance equations in your earlier case, you can just go back and just refer there, that was something else. And how exactly it is going to impact now in terms of the other values, you can see over here. Since Ri and A are large, again remember Ri input resistance has to be large, A definitely has to be large. One more addition, what are the large components in your op amp amplifier? That is input resistance, feedback resistance, and A. A is nothing but your open loop gain. All are very, very large. If that is the case, then this entire term will reduce to R1, because this is the large term multiplied by this large term divided by again a large term, the parallel term will reduce to almost 0. So that gives you what is the input resistance of this particular amplifier with feedback anta keladaga, it is nothing but whatever R1 you have, that is itself is the input resistance of this feedback amplifier. That is RF value will nothing but R1. So this is the idealistic value or practical value or exact value bandaga, this entire thing is your practical or exact value. So this is what is the simple derivation of your input resistance with feedback, and that's the beauty of breaking down a bigger resistance into its smaller components. Fine. And we can just proceed with the similar derivations what we have done. The feedback amplifier, the output resistance with feedback amplifier voltage shunt feedback amplifier. See, nani input resistance helide nimaga, and we have done in the just previous class itself. Yeah, ROF is equal to R0 divided by 1 plus A beta anta ನಾವು ಮಾಡಿದ್ವಿ ಇಲ್ಲಿ, ಹೌದಾ? So that's what we have done over here by arranging some the test voltage over here and shorting the input sources. We have obtained ROF as R0 divided by 1 plus A beta. So the same thing we are supposed to obtain the thing over here when it comes to voltage shunt feedback amplifier. Now that I am going to keep it as an assignment number 2 for you guys. I'm not going to deal with the output resistance of voltage shunt feedback amplifier. I have only taught about the closed loop gain, and I taught about the input resistance with feedback. What will be the output resistance with feedback? You can just refer the textbook, and that will be the assignment number 2. I'm going to mention that in the PDF and I'm going to post it in the Microsoft Teams. So that will be the one of the question for you to write it as an assignment, that is output resistance with feedback for voltage and feedback amplifier. And the concept will exactly remain the same, but difference ಏನಪ್ಪಾ ಅಂತಂದ್ರೆ ಸರ್ಕ್ಯೂಟ್ ಅಷ್ಟೇ ಬೇರೆ. ಸರ್ಕ್ಯೂಟ್ ಬೇರೆ ತಗೋರಿ, ಇನ್ಪುಟ್ ಸೋರ್ಸ್ ನಾನು ಶಾರ್ಟ್ ಮಾಡ್ರಿ, ಔಟ್ಪುಟ್ ಕಡೆ ಒಂದು ಟೆಸ್ಟ್ ವೋಲ್ಟೇಜ್ ಅಪ್ಲೈ ಮಾಡ್ರಿ, ಆ ಔಟ್ಪುಟ್ ವೋಲ್ಟೇಜ್ ಇಂದ ಏನ್ ಕರೆಂಟ್ ಬರ್ತತಿ ಅದನ್ನ ಎಕ್ಸ್ಟ್ರಾಕ್ಟ್ ಮಾಡ್ಕೋರಿ and get a voltage equation and try to obtain the ROF. So that will be the value of ROF. And if I can give you the hint, ROF value will also exactly resemble to that of the voltage series feedback amplifier. You can just closely look, you'll almost get the same equation. Fine. Moving ahead, we have already discussed the implication of gain bandwidth product, and the same implication is acceptable, or it is viable in the voltage shunt feedback amplifier as well, and there is no much difference. And if I can just refer the same derivation what we have done over here, that is FF is equal to F naught times 1 plus A beta, so that is indicating the bandwidth is extended when I use voltage series feedback amplifier. The same thing will be extended over here, and which means I can say that the bandwidth will be extended even if I use the voltage shunt feedback amplifier. So the gain bandwidth product of with a single break frequency, I am going to get as the break frequency as F naught times 1 plus A beta. So this is what I am going to obtain. So this is all about your both voltage series feedback amplifier and voltage shunt feedback amplifier. So we are supposed to next go ahead with the applications of basically the applications of op-amp, which are nothing but your summing amplifier, scaling amplifier, averaging amplifier, and then we are going to talk about the instrumentation amplifier, a simple applications again which you have learned in your earlier courses. We are going to have those derivations, but before that we'll solve two numericals. One is based on the voltage shunt feedback amplifier, that is your inverting amplifier, and the other is based on your non-inverting amplifier or voltage series feedback amplifier. So I have already marked over here which are the things that I am going to solve it in the class. I am going to solve example number 3.1, example number 3.3, which are marked in the text page 84 and 893. I am going to solve it, and assignment questions will be question number 3.1 and question number 3.5, which are from page number 105 and 106. I am going to mention that also in the PDF. So making it all together 3 questions for week number 2's assignment. One is the derivation for output resistance for the voltage shunt feedback amplifier, and one numerical on inverting amplifier, one numerical on non-inverting amplifier, and on the same lines I am going to solve 2 more numericals. In fact, I am going to solve 2 or 3 numericals in the class pertaining to inverting and non-inverting amplifiers. And on top of that, once that is done, we are going to look into the different applications of the op-amp. So let's take the attendance now. Kindly give the attendance. So the attendance code here will be you can just open up your WhatsApp and you can share the link. The code is 2852. Code is 2852. Two 2852. Done with the dance? Please respond.
No, sir.
Do it.
No, sir. No, sir.
Okay, okay, do it.
Sir, code
2852 2852. Done?
Yes, sir.
Yeah, can you see the PDF now? What I have shared here?
Yes, sir.
Yeah.
Yes, sir.
This is a small problem. I'll just try to explain it how exactly we are supposed to solve it. And on the same lines, we'll solve a few more problems in the next class. Fine. This is a problem or numerical from for the inverting amplifier. An inverting amplifier is implemented with R1 equal to 1K, RF equal to 100K. Find the percentage change in the closed loop gain A, where A is the open loop gain, and it changes from 2 into 10 raised to 5 to 5 into 10 raised to 4. So this is what is the thing he has given, and repeat the same thing for non-inverting amplifier with R1 equal to 1K and RF equal to 99K. So basically he is asking us to what is the percentage change in the output voltage in the gain. Fine. So let's try to understand the gain equation for the inverting amplifier, which we have already just now we have dealt. That is A times minus RF divided by R1 plus RF plus AR1, and just simply you are supposed to substitute the values. On substitution, we are going to get the value of AF as here minus 99.9445. So this is for the term R1 equal to 1K, RF equal to 100K, right? And A is for the value 2 into 10 raised to 5. So A, that is open loop gain 2 into 10 raised to 5 iddaga RF istiddu R1 1K iddu, what will be the gain with feedback? I obtain as this one. Next time I'll do the same experimentation for inverting amplifier only when the gain is changing from gain 2 into 10 raised to 5 badly 5 into 10 raised to 4 idda gain agutte. That's what he has asked. So now with A is equal to 5 into 10 raised to 4, what is the value of gain? Again, I'm going to use the same equation. I'm going to substitute all the values. R1, RF won't change, so that will be kept as it is. Now what will be the value of AF? AF is this one. And what is the percentage change? Percentage change is what? The first value minus the second value whole divided by the first value. So that will be the percentage change. So percentage change in the gain is what? 0.15 percentage. And there is a negative sign, that is basically because it is, since it's a non-inverting amplifier, it's a mathematical negative sign, and it is only to indicate the phase shift, nothing more than that. So 2 into 10 raised to 5 open loop gain iddaga ಒಂದು ಕ್ಲೋಸ್ ಲೂಪ್ ಗೇನ್ ಬಂತು, 5 into 10 raised to 4 ಓಪನ್ ಲೂಪ್ ಗೇನ್ ಇದ್ದಾಗ ಇನ್ನೊಂದು ಕ್ಲೋಸ್ ಲೂಪ್ ಗೇನ್ ಬಂತು. ಅವೆರಡರ ನಡುವೆ ವಾಟ್ ಈಸ್ ದ ಮೇಜರ್ ಚೇಂಜ್? 15% of the change has happened. So this is about how you are supposed to solve the numerical whenever it is asked for change in the gain. On the same line, there is a non-inverting amplifier which he has given over here, and the formula is, look here, that's the reason I was talking about the entire formula. You can see over here on top, it is minus R1 times A divided by R1 RF A R1, and below it is R1 plus RF times A whole divided by entire the same thing. So you know the equations I know now. It is non-inverting amplifier. I am going to substitute the values. I'm going to substitute different values, and I'm going to find AF for A equal to 2 into 10 raised to 5. I obtain one value. And what will be the value of AF for A equal to 5 into 10 raised to 4? I'm going to get another value. Percentage change anta bandaga first value minus second value. First value another minus 99.95 minus second value minus of minus. Second idu minus nagada ಇಲ್ಲಿ center nagu minus irutte. Minus of minus that gives you plus. So basically the equation is what? First term minus second term divided by first term into 100 to obtain in terms of percentage. So this is in terms of minus 0.1496 percentage. So it's a very small change in the gain. So intention of this problem, the objective of this problem is to ensure if there is any change in the open loop gain. See, problem, what is that interpretation I'm going to get? The only expected outcome of this problem is that nandu open loop gain ಎಷ್ಟು ಬೇಕಾದರೂ change ಆಗಲಿ. So this is what I have told you in the very beginning of the class. Whatever is the changes that happens to A, that is open loop gain in the circuit, that is not going to hamper the closed loop gain. Closed loop gain ಎಷ್ಟು change ಆಯ್ತು ನೋಡ್ರಿ 0.15% ಅಷ್ಟೇ. It is very less. It is very less. Even it is not even 1% also. So 0.15% ಅಷ್ಟು value ಅಷ್ಟೇ change ಆಯ್ತು. So that is the reason why we go for feedback amplifier. So this is the problem to ensure or to understand the concept of feedback amplifier. So this is what it has given me the result. So this is all about the problem number 1. So in the next class, which I'm going to start at 12:45, because yesterday Suresh has taken my 2 classes. So today I'll be engaging one more class at 12:45. It's not at 1 o'clock. Join at 12:45. So we'll solve some new numericals and we'll start with some applications of op-amp, and then we can wind up the session. So this is all about the today's session, and I hope you have obtained enough contents with respect to today's class. So what we'll do, we'll stop it here and we can continue it in the next class. So this is it from today's, and the one more lecture will be at 12:45. You can join at 12:45. Okay, thank you.